So let's talk about something fascinating, and honestly, a little misunderstood: knowledge distillation. It's this process where massive AI models essentially teach smaller, more efficient ones. But how exactly does one AI pass its wisdom down to another? Well, we're about to find out.
And this isn't some far-off theory, you know? It's happening right now with the biggest names in the game. You've got Google's Gemma models learning directly from their absolute powerhouse, Gemini. Meta is using a giant internal model to distill knowledge into its smaller, more nimble models. And then you have companies like DeepSeek using this very same idea to make their huge models way more accessible. So, that's the big question, isn't it? What does it actually mean for one AI to train another? It sounds like something straight out of science fiction, but the reality is grounded in some incredibly clever computer science. And to really understand how it works, we first need to get a handle on why it's so absolutely critical for the AI world today.
It all boils down to one thing: the relentless, and I mean relentless, race to scale. For years, the mantra in AI has just been, bigger is better. But we're starting to smack into some very real, very hard limits.
We're basically facing two giant walls. First, there's the data wall. We've pretty much scraped the entire public internet. There's not much left, so we need more high-quality data. Distillation helps by letting a massive teacher model generate tons of new, high-quality training data for a student. And second, there's the inference bottleneck. The biggest models, sure, they're super powerful, but they're also slow and just ridiculously expensive to run. Distillation is the way out, letting us create smaller, cheaper models that still pack a lot of that original punch.
Now here's the kicker. This cutting-edge solution, it's not new at all. To really get it, we need to hop in the time machine and go way, way back.
The core concept, which was first called model compression, actually popped up way back in 2006. It then took almost a decade before AI legends Geoffrey Hinton and Jeff Dean gave it the name we use today, knowledge distillation. And now, well, it's an absolutely essential tool for building modern AI.
So, picture it. The year is 2006. Twitter had just launched, and the big challenge wasn't running models on huge server farms. It was getting them to work on these things: PDAs, personal digital assistants, which had almost no memory. Back then, the best models were actually ensembles, which were basically just giant collections of, say, 1,000 individual models all working together.
Obviously, you couldn't cram 1,000 models onto a little PDA, so researchers came up with this really slick two-step recipe. First, they trained their giant ensemble on data with hard labels. Think of it as a simple true or false, like an email is 100% spam, period. Then, they trained one small apprentice model. But here's the trick. It wasn't trained on the truth. It was trained on the averaged-out guess from all 1,000 experts. And this created a much more nuanced soft label, which turned out to be the secret sauce.
And that brings us to the famous 2015 paper that really defined the whole modern era of distillation. This is where we get the teacher-student idea and, more importantly, where we uncover the secret ingredient that makes this whole thing so powerful.
Okay, so this right here is the whole game. The difference between these labels. A hard label is just simple. It says, this image is a number 5, end of story. But a soft label from a big, powerful teacher model, it carries so much more information. It might say, look, I'm 90% sure this is a 5, but, you know, it also kind of looks like a 3, and maybe there's even a little hint of an 8 in there.
See, these soft labels, they teach the student model not just what something is, but also what it's similar to. And the paper gives this extra information a fantastic name. It calls it dark knowledge. It's all the hidden reasoning, the gut feelings of the teacher made explicit for the student to learn from. Pretty cool, right?
Now, if you've ever played around with a language model, you've probably seen that temperature setting. Well, guess what? It came from right here, from distillation. Its whole purpose was to crank up this dark knowledge. By raising the temperature, you can make those tiny probabilities for the wrong answers a little bit bigger, a little more visible, giving the student model even richer signals to learn from. The Hinton paper uses this just beautiful analogy for why this whole process is so important: the life of a butterfly. See, for training, a model needs to be like a larva. It's big, it's complex, it just consumes massive amounts of data. But for actual use, for inference, it needs to be a butterfly, fast, light, and super efficient. Distillation is the process that makes that metamorphosis happen.
Okay, so let's bring it all back to today. We started with Google, Meta, and DeepSeek, right? Now that we understand the theory behind dark knowledge, we can actually see that not everyone is doing distillation in quite the same way.
So when you peek under the hood, a really key difference shows up.
It looks like Google and Meta are doing proper distillation. Their student models are learning from the teacher's full, soft probability distribution across every single possible word. That's how the reasoning gets transferred. But DeepSeek's method is a bit different. They have the teacher generate text, and then they train the student on that finished text. So the label is just the one word the teacher picked, a hard label.
And because that method only shows the student the teacher's final answer, not all the nuance and uncertainty behind it, it's really more accurate to call it imitation or behavioral cloning. It's still a really useful technique for making models smaller, for sure, but it's missing that crucial transfer of dark knowledge that really defines true distillation.
So if proper distillation is so much richer, you might be asking, why doesn't everyone do it that way? Well, as with most things in large-scale AI, it comes down to a staggering, almost unbelievable engineering challenge.
Let's do some quick, scary math. Say your training dataset has 8 trillion tokens, and your vocabulary has about 128,000 words. Well, to do proper distillation, you'd need to store the teacher's full probability for every single one of those words for every single token. That works out to roughly 10 to the power of 18. Values. That's a 1 with 18 zeros after it. It's just an astronomical number.
To put that number into perspective, just storing all of that data would require as much disk space as the entire library of videos on YouTube. It's just not going to happen. It's not feasible, even for the biggest tech companies on the planet.
So how do you solve an impossible storage problem? You just don't store it. This is where Meta's really clever solution called co-distillation comes into play. Instead of doing it in 2 separate steps, they do everything all at once. The teacher and the student are trained at the same time. The teacher generates the soft labels on the fly, the student immediately learns from them, and then poof, they're discarded. This completely sidesteps that impossible storage cost. It's brilliant.
All right, so after that deep dive, let's pull back and really nail down the crucial points to remember about this incredibly powerful technique. First, remember that distillation isn't new. It's a nearly 20-year-old idea that's been brilliantly repurposed for our modern era. Second, the real magic isn't just about generating more text to train on. No, it's about transferring that dark knowledge through those nuanced, soft labels. And finally, the details really matter. How a company actually implements this process is the difference between true knowledge transfer and just simple imitation.
And this all leaves us with a pretty fascinating question for the future. You know, in any teacher-student relationship, the student's potential is often limited by what the teacher knows. So if our AI systems are learning more and more from each other, what does that mean for the ultimate boundaries of AI capability? Are we just creating an echo chamber, or are we building a launch pad for something entirely new?